Today we examine the binomial distribution and specifically look at how to perform binomial calculations in Stata. Before beginning this module, read the example about the Uzbekistan flour fortification program provided for you on this webpage. We're in the setting where, in 2007, suppose we've collected a sample of 100 women of reproductive age randomly from the population in Uzbekistan, and we test those 100 women to see if they have anemia. We're going to define the random variable x, denoting how many of the 100 women that were anemic. Now suppose that the prevalence of anemia in Uzbekistan is 60%. Consequently, we know that since we've taken a random sample, the prevalence in our sample of 100 women should be 60%. The first question we want to ask is, can we model the random variable x using the binomial distribution? In order to answer that question, we need to consider the assumptions of the binomial distribution. First, we know that to use the binomial distribution, we need a binary outcome. Since we're looking at anemia, namely a woman either has anemia or doesn't have anemia, we do have a binary outcome in this scenario. The next assumption is we need independence of observations. We've randomly sampled 100 women. Since we used random sampling, it should be true that one woman is independent of another woman. Therefore, we have independence. Next, we need that n, our sample size, is fixed. I've already told you that we're using a sample size of 100 women. I decided that before I did the survey, so obviously the sample size is fixed. And finally, we need to have the same p, or same probability of anemia for each woman in the sample. We know that there's 60% prevalence for the general population, therefore this assumption is also satisfied. So it's okay to use the binomial distribution to model x. Given that, we can calculate the expected number of women with anemia. The expected value of x is equal to n times p. We have 100 women. The prevalence of anemia is 0.6, therefore the expected value of x is 60. Next, we want to know in a random sample of women in Uzbekistan, what is the typical departure of the number of women with anemia from this mean number? So what this is asking for is, we want to know the standard deviation of x. For the binomial distribution, we know that this is equal to the square root of n times p times 1 minus p, or the square root of the variance. So plugging in our numbers, we have the square root of 100 times 0.6 times 0.4. Plugging that into a calculator, we find that the standard deviation of x is approximately equal to 4.9. All right, so moving on, now we want to do some probability calculations. First, we want to know what's the probability that exactly 60 women develop anemia. The probability that x is equal to 60 using the binomial formula is equal to 100 choose 60 times p, which is 0.6, raised to the 60 times 1 minus p raised to the 100 minus 60. So if you try to plug that into a calculator, there's a good chance that your calculator is going to be very unhappy because this is a really, really big number. So let's look first of all, how would we plug this equation into Stata? Stata actually can do this computation for you. So now open up Stata on your computer. Now that you have Stata open, to calculate the probability that x is equal to 60, you can type the equation into Stata. So to calculate 100 choose 60, you use this comb function in Stata. So I say display 100 choose 60 times 0.6 raised to the 60 times 0.4 raised to the 40th, and I hit enter, and I find that the probability that x is equal to 60 is approximately equal to 0.08. That's probably not the easiest way to address this question. Fortunately, Stata has a suite of commands that makes calculating binomial probabilities very easy in practice. If I want to calculate the probability that x is equal to 60, I can use the binomial p command in Stata. This returns the probability of observing exactly k successes using the notation where x is distributed as a binomial random variable with sample size n, probability p. I would then plug in my sample size, 60, and my prevalence, which is 60%, and it would return this exact probability for me. On the other hand, if I wanted to know the probability that x is less than or equal to 60, I would then use the binomial command in Stata. Finally, if I wanted to know the probability that x is greater than or equal to 60, I would use the binomial tail command within Stata. So let's look at those commands. Open up Stata again. Now before within Stata, we used the actual formula to calculate the probability that x is equal to 60. Now let's use the binomial p function. And fortunately, we end up getting the exact same answer. So we basically did this by hand using the formula to show you that the binomial p function does return exactly the probability that x is equal to 60. Now let's calculate the probability that at least 50 women are anemic. Specifically, we want to know the probability that x is greater than or equal to 50. To calculate this in Stata, we're going to use the binomial tail function. So when you're doing these calculations with binomial probability, since the binomial distribution is discrete, you need to pay very close attention to whether we're dealing with less than or equal to versus strictly less than, or greater than or equal to versus strictly greater than. In this question, they want to know the probability that at least 50 women are anemic, so the probability that x is greater than or equal to 50, so we can directly use the binomial tail function. We find that that probability is 0.98. Alternatively, we could use the binomial command to perform this calculation. And we would calculate the probability that less than or equal to 49 women are anemic. And then we would calculate the complement of this probability, 1 minus this, and we would find that we get exactly the same result, namely that the probability that at least 50 women are anemic is equal to 0.98. We get the exact same result, regardless of whether we use binomial tail or the binomial function. All right, so now we're going to assume that the prevalence of anemia actually dropped after implementation of the program. So we had been assuming that the prevalence was 60%. Now let's assume that we ran this program and it caused the prevalence to decrease to 40%. And we want to calculate the probability that at least 50 women are anemic. So again, we can use the binomial tail function, but we want to change the prevalence to be now 40%. We do that calculation and we find that the probability that x is greater than or equal to 50 when the prevalence is 40% is now very low. It's about 3%. So we've gone from the probability that x is greater than or equal to 50 is about 98% when the prevalence is 60%. Now we see that the probability that x is greater than or equal to 50 when the prevalence is 40% is only 3%. So there's a big difference here. So let's say we went out in the field and we collected some data on 100 women and we observed fewer than 50 cases of anemia. This would basically suggest to us that the anemia prevalence had dropped over time and that it's more consistent with an anemia prevalence that's lower than 60%. So think about this concept, the fact that in statistics what we do is we take the data that we've observed and we try to decide whether or not it's consistent with our hypotheses.